You know, when you boil it all down, the entire world of electronics is really about one thing: control, and more specifically, controlling the flow of electricity. But how in the world do tell a current, something that just wants to go everywhere, that it can only travel down a one-way street?
So, how do you do it? I mean, picture this. You're designing a circuit, and you've got a component in there that's super sensitive. You absolutely have to make sure that electricity flows to it from the power source, but never, ever flows backward. You need to build an electronic one-way street. How is that even possible?
Well, you build it with this little guy, a diode. Seriously, think of a diode as the ultimate bouncer at the door of your circuit. It's this tiny component with one very simple but incredibly powerful rule. Current, you can come in this way, but you are absolutely not allowed to go back out. It's a perfect electronic one-way valve.
Okay, so how does this tiny little gatekeeper actually work its magic? Well, to get that, we need to pop the hood and see how the gate itself is built. And it all comes down to something called a p-n junction.
So, this junction is basically made by squishing two specially treated types of silicon together. On one side, you've got what's called p-type material. Think of it as being full of holes, like empty parking spots just waiting for an electron. These act like positive charges. And on the other side, we have n-type material, and it is just loaded with extra free-roaming negative electrons.
Now here's where it gets really cool. The very instant these two materials touch, those free electrons on the n side look over, see all those empty parking spots on the p side, and they just rush across the border to fill them up. And of course, when a negative electron meets a positive hole, poof, they neutralize each other. This whole rush only happens right there at the border, creating this really thin zone where there are suddenly no free electrons and no holes left at all. It's been depleted of anything that can carry a charge, and this area, the depletion region, now acts like a tiny insulating barrier. This is our gate, a barrier that just forms all by itself and slams shut, stopping any more current from getting through.
And when I say thin, I mean it's almost hard to believe. This gate we're talking about is typically around 1/1,000,000th of a meter thick. I mean, that is some seriously precise microscopic engineering right there, all to create the perfect barrier for electricity.
So here's the crucial part. This depletion region, this gate, it actually creates its own tiny electrical field, its own little voltage. You can think of it like a small hill that the electricity has to climb over to get through. For the most common diodes made of silicon, that hill is about 0.7 volts high. If you're using a germanium diode, it's a little smaller, only about 0.3 volts.
All right, so we've got our gate, and we know it's got this built-in lock. The big question now is, how do we open and close it whenever we want? Well, the answer is actually pretty simple. We just apply our own voltage from the outside.
And this right here is where the magic really happens. If we apply a positive voltage to the P side and a negative voltage to the N side, what we call forward bias, we're basically pushing the electrons and holes towards the barrier. This squishes our gate, that depletion region, making it thinner, and boom, current can flow. But if we do the exact opposite, hook up negative to the P side and positive to the N side, we're doing what's called reverse bias. This yanks the electrons and holes away from the barrier, making the gate even wider and stronger. Current stops, dead in its tracks.
And you know, the source material just puts it perfectly. This whole p-n junction setup, with its ability to open and close on command, it literally acts just like a valve, giving us this incredibly precise, one-way control over electricity.
You know, every electronic component kind of has its own personality, right? A set of rules for how it acts. For our diode, that whole personality is captured in something called its VVI characteristic curve. So let's take a look at this rule book and see exactly what's going on. First up, let's look at what happens when the gate is shut tight, when we've got it in reverse bias. Now, the diode is amazing at blocking current, but it's not absolutely 100% perfect. An incredibly tiny amount, which we call a leakage current, still manages to sneak past the gate. And when we say tiny, we really mean it. For a typical silicon diode, this leakage is measured in picoamps. A picoamp! To give you some perspective, a normal little LED light uses around 20 milliamps. That is 2 trillion times more current. So yeah, for all practical purposes, when that gate is shut, it is shut. Okay, so let's flip it around and go into forward bias. We start pushing on that gate with a little bit of voltage. But remember that built-in barrier we talked about? The diode resists, it pushes back. So at first, even though you're applying some voltage, almost nothing happens, no current flows. You have to push hard enough to finally overcome that internal barrier.
And that specific voltage where the gate finally gives way and just swings open, letting current rush through, that's called the knee voltage. It's basically the unlock point for the diode.
And guess what? This unlock point is exactly that barrier voltage we saw earlier. For a germanium diode, you only need to push with about 0.3 volts to get the gate open. But for our trusty silicon diode, you've got to push with at least 0.7 volts to get things moving.
But here's a most important part. The second you get past that knee voltage, the floodgates just burst open. A tiny little increase in voltage after that point causes a massive surge of current. The diode goes from being basically off to completely on in an instant.
Now, of course, every component has its limits. If you apply a really high voltage in the reverse direction, you're pulling that gate shut way too hard, you can actually force it to break. This is called the breakdown voltage. It causes a huge reverse current, and yep, it usually destroys the diode for good. So this is one limit you definitely don't want to test. So what do we got here? We've got a component that's either completely off or fully on. That on-off behavior sounds an awful lot like a switch, doesn't it? Let's see how this super simple one-way action makes the diode so incredibly useful in the real world.
That's right. That's exactly what it is. The diode's binary nature, it's either blocking everything or letting everything flow, makes it a perfect electronic switch. And you know the best part? It's totally automatic. You don't need to flip it, it just responds instantly to the voltages in the circuit, all by itself.
Okay, check this out. This is a classic, just brilliant application, an automatic backup battery circuit. So when your main power is on, its voltage is actually holding the diode connected to the battery in reverse bias. The gate is shut. The battery just sits there ready to go. But the second the main power fails, that reverse voltage vanishes. The battery's own voltage is now free to push the gate open, forward biasing the diode, and it instantly starts powering your device. There's no interruption, no manual switch needed. The diode handles the whole thing automatically. It's fantastic.
So let's just boil this all down, shall we? The number one thing to remember is that a diode is just an elegant, simple, one-way valve for electricity. And it all works because of that amazing little depletion region, which acts like a self-forming gate. We saw that a forward bias voltage pushes that gate open, while the reverse bias pulls it shut even tighter. And it's this incredibly simple, automatic on-off action that makes the diode one of the most important fundamental building blocks in all of electronics.